Deep in the ocean, there's this hidden world of tiny fungi that are basically powerful, microscopic recycling plants. And get this, they've got a set of molecular tools that could literally change everything, from how we make biofuels to building more sustainable industries. So let's dive right in and explore these amazing ocean enzyme factories.
Just think about it for a second. The oceans are absolutely filled with mountains of tough plant stuff. Seagrass, algae, all of it. Now, on land, we know that fungi are the master decomposers, but the sea, that's a totally different ballgame. So the big question is, what's really breaking down all this material out there?
Okay, so let's set the scene here. Oceans cover more than 70% of our planet, and just like a forest, they are teeming with life. And of course, where there's life, there's also decay. All that tough plant matter, what scientists call lignocellulose, it all has to be broken down and recycled back into the food web. But how does that happen?
And that is the real challenge. The conditions down there are just extreme. I mean, most of the fungi we know from land would just give up and fail. You need a real specialist, something that has spent thousands, maybe millions of years adapting to not just survive, but actually thrive in that salty, high-pressure world.
This is where our scientific detective story really begins. Researchers off the coast of Tunisia went out and they isolated 5 different fungi from the marine environment. They brought these suspects back to the lab to figure out if they had finally found the recyclers they'd been looking for. So here's our lineup. We've got 3 different strains of a pretty common fungus, Trichoderma asperellum. We've got another familiar face, Aspergillus nudulens, and then there's this more unique character, Stemphylium Lucomagnoense. The big question is, which one of these is truly built for a life at sea?
All right, time for the first round of interrogation. The scientists really put these fungi through their paces. They grew them on different food sources designed to mimic plant fibers, and they did it all with and without sea salt to see who could really handle the pressure.
Now this is where it starts to get really interesting. For most of the fungi, when you add salt, that's what you see in the gray bars. Their growth either didn't change much or it even slowed down. But take a look at SLU. That's our Stemphylium Lucomagnoense. When they grew it on a type of cellulose, its growth actually got better with salt. That's a massive clue that this fungus is something special.
Growing is one thing, but recycling is all about the tools you use. These charts are measuring the activity of specific enzymes. Think of them like molecular machines that break things down. I know it looks a little complex, but the key takeaway here is simple. Scientists were comparing how well the fungi could digest a land plant, weed straw, versus a marine plant, seagrass, both with and without salt. And let me tell you, the results from these tests started pointing to a very clear winner.
So after running all these initial tests, looking at both how they grow and what enzymes they use, the evidence really started to stack up. One of our suspects was clearly way better adapted, just standing out from all the others.
And our prime suspect is Stemphylium Lucomagnoense. This is the one. This is the fungus that showed every sign of being a true marine specialist.
Okay, let's review the evidence that basically sealed the case. First, as we saw, its growth could actually improve with salt. That's pretty wild. Second, when it was digesting seagrass, it had the highest activity of a really key enzyme called xylanase. And third, and this is the real clincher, another one of its enzymes, laccase, actually ramped up its activity on seagrass in salty water. It just performs best, right in its natural habitat. So now that the scientists had their prime suspect, they had to go deeper. They needed to see the entire set of tools, the enzymes, that this fungus actually sends out into the world to break down its food.
And this complete set of secreted proteins has a really cool name. It's called the secretome. You can think of it as the fungus's molecular toolkit, right? Just like a chef has a specific knife for every single job, a fungus has different enzymes for different foods and different conditions. And what's absolutely fascinating is that this fungus customizes its toolkit for every single job. This diagram shows us that the set of enzymes it uses for wheat straw is totally different from the set it uses for seagrass. And then when you add salt, the toolkit changes all over again. This is just adaptability in action. It's incredible. Okay, let's look a little closer. When you grow it on a land plant, like wheat straw, with no salt, the fungus basically pulls out all the stops. It deploys this massive toolkit of 50 different enzymes. It's like it's throwing the entire kitchen sink at this unfamiliar food source.
But now add salt. The pressure is on. and the fungus gets way more efficient. It shrinks its toolkit all the way down to just 17 enzymes. See, it just can't afford to waste energy making tools that aren't going to work well in a salty environment.
All right, now let's switch to its home turf, seagrass. Even without any salt, the fungus is already way more specialized. It starts with a smaller, more focused toolkit of 17 enzymes. It's the same number as with the salty wheat, but you can bet it's a different, more specialized mix of tools.
And this just brilliantly illustrates its mastery. When it's in its natural habitat, seagrass plus salt, it is unbelievably efficient. It uses this tiny, highly specialized toolkit of just 8 enzymes. These are the perfect tools for the job, and it doesn't waste a single drop of energy on anything else.
But here's maybe the most crucial detail of all. The fungus didn't just turn enzymes off when things got salty. No, it actually deployed a brand new, special tool that it only uses when salt is in the picture, no matter what it was eating. And that special tool is an enzyme called alginate lyase. Its job is to break down alginate, which is a key component you find in the cell walls of brown algae. This is the smoking gun. It's an enzyme made specifically for digesting marine life, proving that this fungus is a true child of the sea. So, we've solved the mystery of this one incredible fungus. But this discovery, it isn't just a cool piece of science. It's actually a blueprint for some pretty amazing real-world technology. I want you to think about industrial biorefineries, the kind that create biofuels. They use massive amounts of fresh water. It's a huge environmental and economic cost. But what if we could use the enzymes from our marine fungus, enzymes that don't just put up with salt, but actually thrive in it? We could potentially run these entire processes using abundant seawater instead.
So, when we put it all together, what have we learned? Well, we've learned the ocean is home to fungi with these unique, salt-loving enzymes. They are absolute masters of adaptation, constantly fine-tuning their molecular toolkits to be incredibly efficient. And by studying them, we're finding nature's blueprints for greener technologies that could save enormous amounts of precious fresh water.
I mean, this one single fungus, Stemphylium Lucomagnoense, has revealed such a powerful secret. It really makes you wonder, doesn't it? With so much of the ocean still completely unexplored, what other incredible solutions, what other natural blueprints are still down there just waiting to be discovered?